However, the Hoffman elimination, which is its own section, is a very important reaction, right? You can tell Hoffman did a lot of work with bases. He's got 2 reactions named after him in the amine chapter here. But the Hoffman elimination is a very useful chemical reaction. That's where we take an amine and we essentially do an E2 elimination, but what we get is the less substituted alkene. We don't do like a regular E2 where we eliminate to the more substituted position. That was Zaitsev's rule way back in the alkene chapter. No, we eliminate to the side that has fewer R groups. And to do this, we start with just an amine. We react it with excess methyl iodide. And remember how we said that alkylation of amines works? We'll add 1 methyl group, but that's even more reactive. So we'll add another and we'll add another until that nitrogen is full and it's an ammonium. It's an ammonium salt. We got 1 methylpentyl trimethyl ammonium iodide. What happens then? We use silver oxide as a base. Silver oxide is just a source of hydroxide ions that happens to work in this particular condition. It's soluble. We perform an elimination, right? Here's a good diagram of what happens. That quaternary ammonium salt is an excellent leaving group because what it produces is a neutral tertiary amine, right? That's one of the best leaving groups when we can make a neutral compound out of it, right? So it's just an E2, plain old E2 elimination, right? The only interesting part is the formation of that quaternary ammonium. So what happens in E2, the base removes a proton next to the leaving group. So hydroxide attacks that H. The CH bonds become the CC double bond, and that kicks the leaving group off all at once. Okay? It's a concerted mechanism, meaning those 3 arrows happen simultaneously, which means as the hydroxide is approaching that hydrogen, the double bond is forming and the leaving group is leaving. It happens all at once. The reason we eliminate towards the less substituted side is because of steric hindrance. The leaving group is so large that the base really can't approach the more crowded side. Even though we get a more stable alkane when it's more substituted, this large leaving group means that the base can only efficiently access the more accessible carbon. So that means the one with fewer R groups on it, or you can think of it the one with more H's on it, is the one that gets attacked. So if I have this leaving group right here, or yeah, this compound with the quaternary ammonium, the hydroxide is going to preferentially attack one of these less hindered hydrogens, right? Giving us 1 pentene instead of 2 pentene. 1 pentene is produced in a large excess in this reaction. Right? So much so that you could purify it and get that in excellent yield. So if you ever need to do an elimination that eliminates towards the outside of the molecule, right? Usually eliminations happen towards the inside where it's more substituted. So this will eliminate towards the outside. It's a great way of making a terminal alkene. So think of it retrosynthetically. If you have a terminal alkene like that, it can come from an NH2 on the second carbon in, on the inside carbon of the alkene. And then, think back all kinds of more retrosynthesis. If we use reductive amination, that can come from a ketone, where a carbonyl is where that NH2 was. So be thinking backwards retrosynthetically. There's going to be more synthesis on this upcoming exam, so be sure to practice with interconverting those functional groups and being able to identify how to turn one thing into another.